Section 14.8 is Lagrange multipliers. So this is a long section. We're just going to get a start on it today. These problems are quite long and complicated, just to put it right out there. So today we're going to talk about what the Lagrange multipliers method is and do a simple example, which is not going to seem so simple, but relatively speaking it is. And it's actually a problem that we could solve with Calc 1 methods, but again, this is going to provide us a little bit of a background so that we can attack some problems that we definitely wouldn't be able to do with Calc 1 methods. So anyway, in the prior section, we solved absolute maximum and minimum problems in 14.7. So it turns out we are going to be able to solve those problems with this other method, this Lagrange multipliers method, but we're also going to be able to solve other problems as well. And so these can also be thought of as optimization problems. So you may remember optimization problems from Calc 1 or in your classes you've been taking in your field of study. So it's pretty common to solve optimization problems in all sorts of different disciplines because we, for example, in economics would want to know how many people to employ to have the maximum profit or something of that nature. That's something you would care about if you're a business. So having a max profit, that would be a profit function, would be something that you would optimize. And so, and then in engineering, of course, other things too. So it turns out at a high level, when we have this multivariate situation, this Lagrange multipliers method is what's used to solve optimization problems. So this is one of those things you might actually see again, especially I'm told in economics and engineering and applied math. So let's get started. In this one, we're doing an example that's different than what we had in 14.7. 14.7 we had like this domain, and then we were trying to optimize a z based on x and y in that domain, on a closed boundary domain. So anyway, we're going to be able to solve, it turns out, those problems with this method as well, but we can also solve different problems like this. And so we're trying to optimize an equation given some certain constraints. And we'll get started. Find the rectangle of maximum area that can be inscribed in the ellipse given by x squared over 3 squared plus y squared over 4 squared equals 1. And so the picture of that is given here. And so notice this is our ellipse described by this equation. And then having a rectangle inscribed on that would mean that we have some point, which we're going to define in general as xy. And then that would pretty much define the rest of the rectangle if we understand that it's going to make a horizontal line going across and a vertical one down. And that would be an example of one inscribed rectangle. But you can imagine like a slider here and being able to move that point along the ellipse, and then you'd have different sized rectangles that presumably would have different area. Alright, so we're getting started here. What we're trying to maximize is area. We don't even have an equation for this, so usually this is going to be more set up for you, but we're just kind of getting started here. And this is starting out as a motivating example for this Lagrange multiplier method. So anyway, making this the equation of a rectangle, its area, notice that when we have the x dimension here on this red rectangle, that's only half of what I'm going to define as the width. And so the total width here is 2x, and then by that same type of reasoning, y, just being the y coordinate is actually only defining half of this length, then to find the total length, it would be 2y. And then when you multiply those together, you get the area. So we just made a little equation that we're going to try to maximize or optimize, if we want to put it that way. And we're going to call it f of xy, and it's dependent on x and y. And we get 4xy for that. All right, so the x and the y can't be anything. They are constrained to this ellipse. So that's another thing that needs to be included here. Before I get to that, sometimes we call this equation that we're trying to maximize or minimize, in this case the area, the objective function. So now getting into this whole business of the x and y actually be constrained to the ellipse. And so we call this our constraint equation. It's not the thing that we're trying to optimize, but it is something that has to be taken into account, or it's kind of like a restriction. Alright, so now we're going to actually start building this whole idea of a Lagrange multiplier equation in that method. So again, this is really kind of just a motivating example for now. We'll actually end up solving this problem after we get that Lagrange multiplier method out of the way and just kind of instead of proving it, for example. So okay, so just bear with me here. Let's consider this constraint equation to be a fixed level curve, and we're going to define it as g. And notice it depends on x and y. And then we're going to let the objective function equal f of xy, which is equal to 4xy, and that's equal to k. And that's the one that's varying. And so this k is a constant, but if you let it vary, it's like a family of level curves. And so specifically for xy, that function defines a hyperbola. So they happen to be a family of hyperbolas in this case. So look at this cool graphic here on the left now. This graphic is illustrating in this problem what's going on when we describe the family of parabolas. So this is the area function set to some k, and so the k's at the different levels, if you plotted those up, they're shown here. The one with 72 looks like this, the one with 56 looks like this, and they are parts of hyperbolas here. So really what we're trying to do in this problem is we're trying to find the maximum area. Under what conditions do we have this maximum area? When we have that area defined by this family of hyperbolas is constrained to the ellipse that's shown here. Well, that's going to be when that level curve intersects and just barely touches that ellipse. So it's a little hard. Again, these are level curves, so you can see them coming in their x and y coordinates, but if you want, you can kind of try to picture them coming out of the board or coming out of the screen, where a k equals 72 would be higher than the one that's 56, etc. And that's what these would look like coming in. So again, trying to imagine in 3D, and then this ellipse is in 2D, where they just barely touch, so this surface just barely touch at k equals 24. And that's going to be the least k for which we have it touching the ellipse. And so if you think about that in terms of optimization, this is the max area. That 24 is the max area that you can have for the x and the y constrained to the ellipse. And that occurs right at where this red arrow is. If you have ones that are off, level curves that are off, then they're not constrained to the ellipse. And you can imagine them coming in further, and then that max area k would no longer be a max, I guess. It would be x and y for which we get a little bit lesser area than the maximum. So the answer is 24. That is the max area. This isn't actually how we solve the problems because we don't have these cool level curves drawn for us. But observing here what happens when the k equals 24 level curve is just barely touching the ellipse here, notice that they're going to intersect only at a point. And that point and the relationship it has with the curve is pretty special. It is a tangent line. They intersect here at this point, and they both have the same tangent line. Both of those curves have the same tangent line at that point. So that's what this is all trying to show, because it turns out that's true in general. And then we can use some properties of tangent lines at a point to come up with this whole Lagrange multipliers technique or method. So here's where we're going with that. So I kind of described this stuff already. So here's the property. Two curves tangent to one another at the same point, or let me restate that. Two curves are tangent to one another at a point. I need an R in there. A-R-E. I'll fix that when I'm done with this. If and only if their gradient vectors are parallel. Alright, so it turns out this is a really key observation or thing to connect here with this problem. Back in section 14.6, we talked about gradients, and you can maybe appreciate some of this from that, but I'm not going to go into details there. With our knowledge of vectors, gradients are vectors, and so if we were to write that relationship down with notation, it would look like this. The gradient of f is equal to lambda, which is a constant, times the gradient of g. And so, again, these are vectors, and when they're parallel, then this relationship holds between vectors. This is something we learned back in chapter 12. So that special lambda constant is the Lagrange multiplier. That's it. That's the Lagrange multiplier. And so it turns out, I mean, this seems like, why would that help at all? But it turns out it does help, and it can be generalized, like really big, and used in all sorts of different situations, more than just what this example would imply. Alrighty, so now let's get to how this is helpful. And this is the method of Lagrange multipliers. To find the maximum and minimal values of f of x, y, z, so we can, turns out, just scale this up to even more dimensions. Subject to the constraint g of x, y, z equals k, assuming that these extreme values exist and the gradient of g doesn't equal 0. On the surface, g is equal to k. Alright, first thing, find all values of x, y, z and lambda such that we got that equation. The gradient of f is equal to lambda times gradient of g. And that our constraint, that equation g is equal to k. Alright, then once you do that, so there's a bunch of, you basically solve systems that result from these. You're going to get a bunch. You're going to get one for each component here that has lambda in it, and then usually you kind of do algebra jazz or improv algebra there to solve those systems, and then kind of relate it with this constraint. Or so it's been in the problems I've done so far. Next step, evaluate f at all the points, x, y, and z, all the solutions you find here, those are like your candidates for the absolute max and mins. And then you plug them in, just like we did in the prior section, 14.7 at the end, to see where do you get the biggest output. Where do you get the biggest f? Okay, that's going to be the absolute maximum is attained there. Absolute min is when you get the smallest value. Alright, so this example, motivating example, turns out is exactly the same as this example 1, but this is stated in a way that you don't have to do as much setting up. It says find the maximum value of f of xy equals 4xy where x is greater than 0 and y is greater than 0, subject to the constraint x squared over 3 squared plus y squared over 4 squared equals 1. Alrighty, so the first thing is define your f and g. The f is already defined, but if you look at this whole Lagrange methods, Lagrange multipliers method, your g is the constraint, and the thing that you're wishing to max or minimize is f. So make sure you got those squared away. So we're already given that 4xy, which again was the area of that rectangle. This is what we're trying to maximize. And then we call that objective function. And g of x is the constraint function, which in our case was this ellipse. A little weird thing with this one is it also equals 1. If you look at this in the context of how we're going to use it with the Lagrange multiplier equation here, when you don't have to worry about letting, like how do you include the 1, you don't have to worry about it because it turns out when you take the gradient, or those partial derivatives with respect to x and y, the derivative of 1 is 0. So you can be kind of move on at this point. So like I said before, you use this equation to get a system of sometimes a whole lot of equations. Solve those. Systems are the candidates for the absolute max or min. Depending on what you want, plug in the candidates to f of xy to find which yields absolute max or min. Okay, so I should have been clear that we also need the constraint in here. Maybe I'll go back and put that in just to be clear that that's another one of our equations in the system. Alright, anyway, so let's start finding the gradient of f and gradient of g. Typically this is not too hard. So our functions here, f is 4xy, so when you take its partial with respect to x you just get 4y, partial of that with respect to y is 4x, and then we write that as a vector. The gradient is a vector. So we are all set to go with that one. For your g, the equation for g was of that ellipse. Oh, right here. I have it right here. And so when you do the partial with respect to x, you bring down the 2. Constant stays for y, and then this, when y is fixed as a 0, kind of switches behavior here when you have your partial with respect to y, this derivative when x is fixed at 0, and then here we get the 2 coming down and reducing that constant to 1/8 times y. So now we can set up our Lagrange equation, and notice if we look at it component by component, like parametric style, then we get 2 equations. So they have x and y in them and lambda. And then here we have also the constant equation. Overall, these are the system of equations that we're trying to solve. So in this case, it does make sense to try to relate these first and essentially eliminate lambda, which means that you would solve for lambda in one of them and plug it into the other one. So it really doesn't matter, but I chose to solve this left-hand one for lambda, and then put it in the second one for lambda, and then you get an equation here, not in terms of one variable, but 2, but at least you eliminated lambda. Alright, so here now we have an equation in terms of just x and y, and notice that our constraint equations also just in terms of x and y. They're nonlinear, but if you compare them, you can notice maybe that they both have x squared and y squared in them. So if we just solve this equation down here that's circled for either x squared or y squared, then we could plug it into this one and get it down to one variable. So doing that, sub in, here we get finally our equation in terms of one variable that can be solved without too much difficulty. And so you get y is equal to positive or negative 2 times the square root of 2. Alright, so there was a little extra thing at the beginning that our x has to be positive and our y has to be positive. So we're actually going to throw out that negative answer and just stick with the y equals 2 times the square root of 2. Now we can plug in to one of the equations up above. This one's fine. X squared equals 9 over 16 times y squared to figure out what the corresponding x would be. So we do all that work with our 2 times the square root of 2, and we do get a positive or negative 3 over the square root of 2. And again, because x is just positive, we throw out that negative answer, and so we just have x equals 3 over the square root of 2. Alright, so that's good. What this means is we only have one point that's a critical value, like critical point. And so that's probably pretty much our answer, is how this will work. But let's plug it in and see what we get. So it's a good sign that we get a positive area, 24. To convince yourself, you could maybe pick some points around it, but it's, you know, these are long enough. There's one critical value, it'll work. Wouldn't give you the ones where that wouldn't work because that'd be kind of cruel in the context of Lagrange multipliers. So anyway, notice we get that 24, which was shown in the motivating example, and this is how much work it is to actually obtain that answer, but I just set it up in that way to show you kind of the motivation for what the overall method is for Lagrange multipliers. And so now we can take that Lagrange multiplier method and do all sorts of problems with that, but we'll wait until next time for that one.